So I'm going to try and explain quantum computing and specifically Simon's algorithm and as simply and intuitively as possible. So Simon's algorithm is one of the few algorithms in quantum computing that is both easy to understand while also remaining practically useful. And so the first thing we have to do to understand quantum computing is to talk about a qubit, which is the simplest thing in quantum computing. And so let's represent the qubit as this deck of cards. And in this deck of cards, the probability of pulling a jack is 100%. So we could represent this deck as on some number line. And the axis of this number line is the probability of a jack. And so this would go from 0 to 1, and we would find this deck firmly placed on this point of 1, 100% chance of pulling a jack. Let's also think of a king. If this deck is only kings, we would have some other number line, which is the probability of kings. And so this would go from 0 to 1 and have a 100% chance of drawing a king. But let's say I said this deck is a 50% chance of drawing either. Okay, fair enough. We have a 0.5 chance of drawing a king, 0.5 chance of drawing a jack. However, we need two number lines to represent this one deck. So let's just use a two-dimensional number line or a two-dimensional vector space. So this vector space would have an axis for probability of jack and probability of king. And there's always a 100% chance of drawing some card. So you get a unit circle or a circle with radius 1, and some point on this circle would be defining some deck. And 100% chance of jack would be here, 100% chance of king would be here, and it's a 50-50. You get this 45-degree line. And again, this has a magnitude of 1. And the probability of these would be equal. Okay, fair enough. Now imagine we have two decks, a red deck and a blue deck. Well, if this deck also has a 50-50 chance, we can just come up with some other vector space, which is going to be identical. P king, P jack, and sure, now we have this deck down here and this deck up here. Okay, but what I really want to talk about is some hand, the probability of some hand. While you can treat each hand draw individually, so this would get mapped here and this would get mapped here. What I really want to do is talk about the entire hand with a single model. So same as we did the two axes, gave us a two-dimensional vector space, these two vector spaces is going to give us some four-dimensional space. So we can apply what's called the tensor operation. And so before we even talk about what a tensor is, let's just talk about what are the possible hands that can be drawn. So we can have a blue jack, or a blue king, with a blue king. And then this red deck can either be a red jack or a red king, red jack or red king. So these are the four possible hands we can draw from two decks of jack and kings. The probabilities are going to depend on the distribution. If both of these are only jacks, we will have a 1 here and a 0, 0, 0 here. Okay, so these which are the weights. So these are the actual basis vectors, and then they're multiplied by some weight. Now let's kind of dive into that for a second. So imagine if we had the probability of jacks. So jack, blue jack, and a red jack. And we also have the probability of a blue jack and a red king. But we also have to think about the probability of a blue king and a red jack, or the probability of a blue king and a red king. So imagine these are all orthogonal axes. This is the vector space that can capture a given hand from two given decks. Or I'm saying the probability of drawing some hand from two given decks. So again, if these were both jacks, you'll find your vector at this point in the vector space, probability of 1. If this is only jacks and this is only kings, you'll be down here. And any combination of any two decks will give you some point on here with probability 1. So it's kind of like a four-dimensional sphere. Okay, hopefully you're still with me. But let's try and apply some rule set to these hands. Because a hand not all hands are equal. So let's just say in our game, if you get a blue jack, you get a point. Okay, so let's say, blue jack, blue king, red jack. Okay, and instead of thinking about jacks and kings, let's just abstract this for a second and say jacks are zeros and kings are ones. So 0, 0, 0, 1, 1, 0, 1, 1. Okay, nice and easy. Okay, and like we said earlier, a blue jack gave you a point. Okay, so these are gonna be our points. So a blue jack gives you a point, and a blue king makes you lose a point. Okay, fair enough. Now let's say a red jack gives you a point. Okay, so you get a point here, and you get a point here, and you'd lose a point here and here. All right, now let's say a different rule set. Each one of these, there's a different rule set. So this is rule 1, rule 2, and rule 3 would be if you have two of a kind. So you get a point here, you lose a point, and a point here. And I'm gonna make the argument that these are the only two rule archetypes, let's call it. Because if you wanted to say, hold on, let's say that a blue jack made you lose a point and a blue king gave you a point. Well, your rule would look like -1, -1, 1, 1. And I'm saying these two things are so similar that you can treat them the exact same. But what is actually similar about it? And the similarity exists in the periodicity. This is only one space away. And so I'm going to say that the periodicity of rule set 1 is going to be 1. And the periodicity of rule 2, so you have 1, -1, 1, -1, that periodicity is 2. And now the third one is a little trickier, right? Because you have 1, -1, -1, 1. So it looks like you have a periodicity of 3 here and a periodicity of 1 here. But let's just kind of expand this pattern and see what happens. So -1, -1, -1, -1, 1 to infinity. Okay, so if we had this thing, we go 1, 2, 3. Oh, we get a -1. Okay, this thing, 1, 2, 3. Oh, we have another -1. This, 1. So we can actually indeed say that rule set 3 does have a periodicity of 3. Okay, well, first of all, so what? And second of all, how do we actually even capture these rule sets easily? Because right now what we have to do is we have to count, okay, when do we see the equal likelihood thing? Well, let's just think about how we can take some hand and rule set combination, which would be, this kind of matrix, this big matrix right here, and map it to a transform. Well, we want to capture each rule set equivalently, because these are all different rule sets. So let's just think about the Hadamard transform for a second. Let's just back up and talk about the Hadamard transform. So the Hadamard transform is a very simple transform. And all it's doing is it's taking some vector and you're going to add the components and you're going to subtract the components in some way. And so a two-dimensional vector, you're going to add, because you have component 0 and component 1. You're going to add component 0 and 1. And then you're going to subtract component 0 minus subtract component 1, which gives you kind of like the similarity between the two components of the vector and the differences between the two components of the vector. And that's what the Hadamard transform is on the root level. So in the case of having a single deck of, let's just say, all jacks, we're going to have 100% chance of a jack, 0% chance of a king. What this is going to do is you're going to apply 1, 0 to 1, 1, which is going to give you 1, and then 1, 0, -1, which is going to also give you 1. 100% chance of a jack and 100% chance of a king. Well, that's not possible, so we're going to do a unit vector here. So we're going to find the magnitude of this vector is equal to 1, and you'll find that you'll get a deck of equal likelihood chance of a jack and king. So similar to, equal jacks, equal kings. So we're transforming, only jacks to jack and king decks. But how does that find the periodicity? That still is not completely clear. Well, let's kind of go to the system of looking at a hand. So we kind of have to expand this transform, and the way we expand it is we just follow the pattern. So we have 1, 1, 1, negative 1. So let's treat this whole matrix as a 1. So this would be 1, then 1, 1, 1, negative 1. Okay, and then 1, 1, 1, negative 1. Okay, now we have to do negative 1 here. So the negative 1, negative 1, negative 1, 1. And so you see it's kind of like a fractal pattern. And if you did this again, you'd go 1, 1, negative 1. And so you'll just multiply this matrix by 1, put it here, multiply this matrix by 1, put it here, multiply this matrix by negative 1, put it here. And this pattern extends infinitely. It's a fractal transform. So if we have this transform, I'm making the argument that this finds the bitwise periodicity of some given hand. So let's take this rule set. So we have this rule set 1, 1, negative 1, negative 1. Well, the first thing you might notice is that this vector can be found right here. This transform is made up of the different rules. And the only rule that you don't find is this one. But in this rule, you get a point for all possible hands, which is kind of violating the principle of what's called a 2-to-1 function. So you might have noticed that in each one of these different rule sets, you get a point for exactly half of the hands. So that's called a 2-to-1, or in this case, you get a 4-to-1, but it simplifies to 2-to-1. And so with some 2-to-1 function, you get that periodicity I was talking about. And if you don't have a 2-to-1 function, you get no periodicity. And you'll notice there's no periodicity in this first vector. Okay, so if we apply this rule set to this transform, what do we get exactly? Well, it's going to give us, 1 plus 1 minus 1 minus 1, which is 0. And then 1 times 1 minus 1 minus 1 plus 1, again, that's 0. And then 1 plus 1, minus 1 times minus 1 is 1. So another 1, we get 4. And then we get 1, 1, negative 1, 1, negative 1, which is 0. So you'll notice that there's only one single vector in this, but after we transform this rule set by this matrix, we get a vector with only one dimension. Essentially, this, we would call that the king-jack dimension. So what I'm saying is after you apply this transform, only one basis survives, which is telling you that this point system is periodic in this way, the 1, 1, negative 1, which would be this way, which would map to this vector, so right here. So this and this are mapped together. And what exactly do I mean by this and this are mapped together? While you have some hands, which periodicity do I have to apply to get the exact same point value? So we have 1 for 0, 0. If we have this periodicity, we would go from 0, 0 to 0, 1, give us that same hand, and then 1, 0 to 1, 1, which would give us this other hand. So this is the periodicity. So each one of these is a different periodicity. So this would be periodicity of 1. This would be 2. This would be 3, because this is 2. Okay, so how exactly do we implement this algorithm? So we kind of talked about how the Hadamard transform finds the periodicity. We talked about how the Hadamard transform can also turn one deck into another deck. So it sounds like the Hadamard transform is doing a lot. So let's just kind of investigate what's happening here. So let's just start with the simplest possible case of two different decks that are all jacks. So, we have, maybe a red deck jack and a black deck jack. or blue. They're two different decks and they're only jacks. We're going to apply the Hadamard transform to each one of these. So we can kind of imagine this is turning this into a 50% chance of getting a Jack King, and this is a 50% chance of getting a Jack King. Sure. And then we're going to apply some rule set to it. Some 2-to-1 rule set. Now, this rule set kind of needs a place for the point values to live, because we only are giving it the hands, and it has to think about the point values as well. So we need to give it some sort of data to do that. So let's just give it these kind of empty qubits, just some Jack qubits. Okay, a little hand wavy right now, but hopefully this will clear up in a second. So we now are applying this rule set. In the same way we had, the hands and the points, we are giving it hands and we're giving it points. And the rule set defines how the points work. Okay, so out of here, we get the combination of hands and points. So some hand is mapped to some point through you. So right now, these decks are going to have that mapping, just intrinsically. And so in order to find the periodicity of that mapping, we're going to apply another Hadamard transform. And we can kind of think of this as one big Hadamard transform. In actuality, these are identical. And then we don't need to do anything with the point system because it's actually kind of already been mapped up here. So we kind of just leave this be. So after we figure out the periodicity with this Hadamard transform, we can then measure it. And similar to how when we had this vector like this, when we measure it, there's a 100% chance of getting of this basis and 0% chance of getting any other ones. But that's because we have a 2-qubit system, 2 decks. In this Simon's algorithm, it needs n minus 1 measurements. So if n is 2 here, minus 1, we get 1 measurement. So with a single measurement, we immediately know which basis of Hadamard transform got lit up by this rule set, or which periodicity we're looking at, because each column vector, or each row vector, depending on how you want to look at it, of the Hadamard transform is mapped to some periodicity. So with only 1 measurement, we can find the periodicity. So, which is really interesting, because now when we measure, this King Jack, again, this is a King Jack basis. If we measure, a King Jack with a single flip of these decks applied to this rule system, we get a King Jack, and we immediately know what the rule system is. We know the periodicity of the rule system, which tells us a lot about the rule system. Which honestly should kind of blow your mind, because normally we would have to do multiple measurements to figure out exactly what the periodicity of the rule system is. You would have to know, does the red Jack give you the point system? Is it the black King that gives you the point system? That gives you the point. But because we're thinking about all possible hands at once and all possible ways this rule system can give you points, we are doing constructive interference to essentially cancel out all these other hand point combinations, which should be pretty interesting in my opinion. But if we go with more decks, if n was equal to 3, we would need 2 different measurements, because the Hadamard transform would have multiple sort of things that are lit up, because the number of possible hand combinations does not exactly equal the number of different periods, if that makes sense, because each one of these hands strictly maps to some period, which isn't necessarily the case with the 3-qubit system. So you need more measurements. And I would explain that more, but I'm running out of time. So that is Simon's algorithm. It's one of the simpler algorithms to explain, and it is actually useful because with any periodic 2 to 1 periodic function, we will get some L, some periodicity. And if we don't have a 2 to 1 function, if it is a 1 to 1 function, we will get a periodicity of 0, which tells us that this is not a 2 to 1 function. So not only does Simon's algorithm tell you the periodicity if there is one, it will tell you if there is no periodicity at the same time. So it's actually quite useful in several different applications.